Hello everyone, I am a master student from South China University of Technology. It is a great honor to present here with our paper Multiple Model-Based Defense for Deep Reinforcement Learning Against Adversarial Attack in the 13th International Conference of Artificial Neural Network. My presentation will include three parts. First, I will introduce some basic information about reinforcement learning and adversarial attack. The second part is about adversarial defense against deep reinforcement learning. Finally, I will introduce our method and the experimental results. First of all, what is reinforcement learning? Reinforcement learning is an area of machine learning concerned with how agents ought to take actions in an environment in order to maximize the cumulative reward. As the figure shows here, an agent takes actions based on the current state of the environment. Then the environment goes into a new state and obtains a reward signal, which will be feedback to the reinforcement learning agent. Video games are a typical scenario for reinforcement learning. Let's take the shooting game as an example. The agent stands for the AI player who observes the state of the game and take corresponding actions based on its own policy, whether to shoot or to hide. Once the AI player hits the target, it will get a positive reward. On the contrary, if the AI player is hit by the enemy, it will get a negative reward. Agents and the environment keep interacting with each other until the end of the game. The overall performance of the agent depends on the cumulative reward which the agent obtained during the entire process. The last decade has witnessed the rapid development of deep neural network. Thanks to the deep neural network, deep reinforcement learning agents are able to handle complex environments, so it has been applied in many applications. Then I will introduce adversarial attack. Adversarial attack is a kind of attack where the attacker tries to mislead the output of the target model by perturbating the clean sample in a specific way. For example, adding some noise. Usually, such perturbations are too small to be visible for human eyes. Some defense methods have been proposed in order to reduce the influence of adversarial attack to deep reinforcement learning models and can be divided into three categories: data modification, model modification, and external models. Feasibility is a concern for both data and model modification methods, since retraining the target model is required. The new models may perform worse than the original ones, especially when the attack is absent. That is, the general performance may be sacrificed for the robustness. As a result, our study focused on the third type of defense methods, which relies on an external model. The only existing model using external model in deep reinforcement learning is named foresight. It predicts the current observation according to the multiple historical observation and the last action by an action-conditioned observation prediction model. An observation considered contaminated based on whether or not it has a larger difference from the prediction. The contaminated observation is then replaced by its predicted one for decision. As we mentioned before, current defense method mainly relies on the one external model. That is, both contamination detection and action correction relies on an observation prediction model. As shown in the figure on the top, the red block stands for the observation prediction model, which is used for state correction. The detection task is a simple comparison between the obtained state and the corrected state, as shown in the green block. However, predicting an observation accurately in reinforcement learning is difficult, since the comprehensive understanding of an environment is required. Inaccurate prediction will cause both incorrect detection and correction, which means the mistake will accumulate. Our study devised a multiple model-based defense method for reinforcement learning, as shown in the bottom figure, which consider the detection and correction tasks separately. Compared with the single model-based method, our multiple model-based method avoids the accumulation of mistakes in detection and correction tasks. Moreover, as both detection and correction tasks are simpler than observation prediction, a simpler model structure can be used. Thus, simplicity is another advantage of our multiple model-based method compared to the single model-based one. Then we analyze the defense performance on single model and multiple model-based defense method. Let P, COR be the accuracy of the only model used in the single model-based defense method, which quantifies the probability of the corrected and original action being the same. The defense accuracy of a single model-based method, ACCS, is calculated as the first formula. On the other hand, let PDT and PM, COR be the detection and correction accuracy respectively for a multiple model-based defense method. Let alpha be the attack ratio defined as the probability of attack. The detection model first determines whether a state is contaminated, and then the correction model corrects the contaminated state. The overall defense accuracy of the multiple model ACCN is defined as the second formula. Here, we assume P COR equals PS, COR equals PM, COR for discussion, since their corresponding tasks both aimed at correcting the actions. In other words, the model used in the single model-based method can be used in the correction task of the multiple model-based defense. By considering the formula above, the relation between the accuracy of the single model and multiple model-based defense method can be shown as the third formula. The figure in the right represents the relationship between the ACCM and ACCS under different attack ratio alpha. Since the detection task is generally simpler than the correction task, it is reasonable to ignore the gray triangle region in this figure. By By considering the triangle area under the diagonal, the area below and above the line can be denoted by AB and AA respectively. AB contains pairs which cause ACCMs larger than ACCS, while AA contains the ones which cause ACCM larger than ACCS. The size of AB is much larger than AA, where alpha tends to be 0. This means that even slight improvement of the accuracy of detection model from the accuracy of the correction model will cause the ACCM larger than ACCS. This analysis indicates that multiple model-based defense is more suitable to deal with attacks with a smaller attack ratio compared with a single one. Next, we will introduce our detection model and correction model. Our detection model aims to distinguish the clean state and the adversarial states. A state containing a number of observations captures the response of the environment in a sequence of time. However, most adversarial attack methods do not consider the time continuity when crafting the adversarial sample. As a result, the observations in the adversarial state follow different distributions with the ones in the clean state. Our detection model aims to capture the difference of the observation distribution between the adversarial and clean state. In our detection model, a feature map named correlation feature map is proposed to extract the consistencies of the observation in the temporal sequence in the state in our detection model. The feature map of each observation of a state is first extracted independently based on the target model. First, for each observation in a state, we need to block the information of other observations. For example, to extract the information from observation xi, a state xi is generated by setting all the values in st to 0 except the one in the xi. Then, we use the mth layer of the target model to extract the feature map. We propose a correlation feature map defined as the stack of feature map of all observations. Here, the last convolution layer is chosen for Fm, since it preserves the more information and contains more features compared to other layers. The figure shows the generation process of the correlation feature map. A detection model is trained to distinguish clean states from adversarial ones based on their CFM differences. First, we collect a dataset containing clean state and adversarial state. Then, the detection model is trained with a logistic regression function. Our correction model aims to map the output of adversarial state to the proper actions. The model only handles the states that classify as contaminated, which makes the correction task simpler since the characteristics of the clean and adversarial state are different. The first step is also the dataset collection. Here, we use the same dataset with the detection model. Then, The correction model is trained with the regression loss, which aims to minimize the difference between the output of adversarial state and the corresponding clean state. Finally, we show the experimental results of our method. The performance of our proposed defense method and other three methods are discussed. The figure shows the average cumulative reward of defense method under FGSM and CWL2 attacks with different parameters. When the attack method in training and interference are the same, our method outperforms significantly than other all methods. Our method performs slightly worse than Foresight in freeway. Foresight has excellent performance in freeway, but not in Pac-Man and sequence, because the environment of freeway is the most simple. Even when the attack method used in training and interference are different, the performance of our models is still satisfying. This result confirms the efficiency of our defense model against adversarial attack. Thanks for listening. If you have any problem, please feel free to send an email to me on this email address.